So in this video, we will be using the Radford-Rice equation we derived in the last video to perform a fixed TP flash calculation for a feed of 4 mole per second benzene and 6 mole per second toluene with the flash drum set at 393 kelvins and 150 kilopascals. So we can start off by just putting in some of the things that we know just from the problem, like the temperature. It said was 393 kelvins, 393, and then it also told us the pressure, which will be at 150,000 pascals. And then we also know the flow rate going in is 10, the total flow rate, and then the individual mole fractions as well we can put in. I'm just going to call that Z, and it will just be an array of the two mole fractions. So it'll be 0.4 and 0.6, because of 4 divided by our 10 and 6 divided by 10 will be 0.4 and 0.6. And then one last thing that we can put in here is our K that we found over here, which is just the pure saturation vapor pressure divided by the pressure. So how we're going to write that in here is P dot PVAP at our temperature divided by the pressure. And those are just some of the knowns that we need in order to start solving this problem. So how we're going to solve this problem is actually going to be using the SciPy root solver. And we're going to be using our Radford-Rice equation, obviously, and setting it equal to 0 and trying to find our v. So we can define a function for the Radford-Rice, I'm just going to call it RR. We'll be inputting a vector into that. And we're going to have one single unknown, and I'm just going to call it like E, and that'll be the first index in our vector. And then we're just going to want to return our sum here that we have for our Radford-Rice equation. So that'll be numpy sum and just going to put a lot of parentheses here just to make sure I don't mess this up. So it's K minus 1 times our Z and then all of that over, and our V over T is what we're signifying here with E. So that'll be over E times K minus 1 minus 1 and then plus 1. And this all needs to be in parentheses. There we go. So this is going to end up being the function that we will be using our root solver on. So now we can use our root solver. And one thing that I forgot to do is that we will want this to be an array. So our root solver is going to run through this for values of E until it equals 0. So this is going to equal E, and we're going to do the root solver of our function right here, RR, and then we just have to supply a guess, like 0.8, and then we're going to want the X attribute and the first index. And that is going to help us get our future values that we want to solve for as well. So now we can start writing equations for some of the unknowns that we are trying to solve for. So first it'll be the flow rate of the gas coming out of our tank. And what that'll equal will just be our feed times our E value. And then for the same for the liquid, it'll just be our feed minus whatever we get for the gas. And then now we can solve for the mole fractions. So we can just use this equation here to tell that our y will just be equal to x times k. And then we just need to define x as well, which our x is just going to use this equation here, which is a lot like our Rashford-Rice equation, but it just doesn't have this ki minus 1. So I'm just going to copy it and paste it from up here. And take out this k minus 1. And then I'm just going to run all to make sure that it processes everything. And then we're going to take a look at what our answers are. So G L X Y and E as well. So these will be all of our answers for the flow rates and outgoing flow rates and the compositions of our vapor and liquid phases right here.